and things keep working. Okay, we are live. So again, everybody, welcome to the Architectural Machines workshop. This is part of the DigitalFutures 2020 initiative, a very, very interesting initiative led and thought by Neil Leach, who very kindly invited me to do this workshop. And it's my first time I'm doing this on remote, on Zoom and live streaming. I've done live streaming before. In fact, there are a lot of my lectures, all in Italian, unfortunately, on YouTube. But let's see how it goes. I've set this up to be quite experimental. So there are going to be, for sure, some kinks, some things we can iron out in the future. It's sort of a test bed for some things I've been cooking up in the last months, both, let's say, both from a theoretical standpoint and on a practical standpoint, with developing some tools specifically for the occasion. They are going to be quite rough, so I hope you will excuse me if things are not exactly as smooth as I would love, but in the spirit of sharing learning and sharing knowledge with you, and hopefully actually taking back some knowledge from you in the way you're going to develop things. I hope we're going to really just have a cool time together and spend some interesting hours learning from each other. So without further ado, let me introduce myself a little bit for those who do not know me already, maybe. My name is Alessio Irioli. I am from Bologna, born and raised, and now I live here. I am one of the co-founders of Computational Design Italy, in short, Codate. The other two co-founders are Andrea Graziano, which is still my working partner, and Davide De Giudice, who is currently since a few years, since several years, is architect at Zaha Hadid Studio now. During the years, when Codate started 10 years ago, and during the years we have incorporated many people in our research. Some of them have become stable collaborators, others have just collaborated with us on an on-project basis. But Codate is not exactly an office or a studio. It's more like a hub for people interested in computation and the application and consequences of computation in several disciplines, all geared towards open-ended explorations. So all of us, we started from architecture. So the obvious first applications were architecturally driven or design driven. But then during the years, we collaborated for the most diverse projects from graphic design, medical application, biocomputation, and printing living entities like mycelium. This was a collaboration we did with Officina Corpuscoli and Maurizio Montalti. We collaborated with medical staff research for prototyping a tool for data representation for medical applications. So there is really an open horizon where competencies that we gain in one field can really prove useful in many other disciplines. So we really believe in this transdisciplinary approach, where it's not just the coming together of specialized knowledge that exchanges things, but we navigate the territory among or between disciplines, trying to find something that it's actually can give birth to some new kind of applications. So coming to my other side, is that I teach architectural design at the University of Bologna. I am a researcher there. The title would be aggregated professor because I have a stable position there. And you will see also some examples from my students from the last year, because we are carrying on kind of a premise or a side application of what I'm just about to tell you. That will be the core topic of the workshop. So coming to that, architectural machines is related to, let's start with the definition of what I think we should define as machine. Machine is, in general, philosophically speaking, just a finite set of operations. So it's not necessarily physical things made of cogs and gears or made of metals and cables. It can be just declined into any form of material system, provided that it performs certain series of operations. And it shouldn't be confused with the mechanical paradigm, where the mechanical paradigm is something that has a linear development from the premises to an end goal. But machines can also have some operations like self-reproduction. So you can have some sort of self-reproducing machines. This was actually something that was thought by John von Neumann in the 60s. And was one of the premises that led to the exploration of emergence, actually. But coming to our more restricted topic, the idea is to explore the nature of thinking like a machine or thinking with machines in architecture, which also includes how do you deal with or how do you think and design things for something that is in the perspectives of today, or can be heavily automated, or has a heavy amount of automation, both in the production and in the thinking. Especially the thinking part is what interests me the most. So to make a brief history of the interaction between automation machines and architecture, there are a lot of things that I'm sure a lot of you might know already, but I just want to, let's say, make this introduction so that you are aware of what is my perspective on things, and you can focus better on the topic. So this was Thomas Edison's patent for a single-pore concrete house from 1908. So the idea of automating construction started very early in the process, and this was like a kind of first thought. There was a very, very high initial investment in equipment, so the technology did not stick for long, because it was really, really a heavy investment. And then you have an entire cast for a single house to do it in a single pouring moment. So it was thought about making construction efficient, but with a model that was still based on a repetition of a unique object, that object was going to be repeated forever. And same thing for something that came up later, which was called houses while you wait, this time heavily relying on prefabricated elements. It was 1946. It was like a huge machine that was going around and assembling a house in like 24 hours. So it could just go along the road, stop, build a house, move to the next position, build another house, same house, and so on and so forth. But machines started from this kind of actual immediate practical applications. And when you think about it, there's a lot of interesting movements from the material dimension to the abstract dimension. Conceptually, a lot of things evolved starting from material practices and then gained levels of abstraction over time, over development, over research. And that is the case of the relations between construction and the beginning of algorithms. So this is an illustration from a book on Greek and Vedic geometry, which is quoted in an article by Matteo Pasquinelli. And the article is very interesting. It's called 3,000 Years of, well, I don't remember the title, but I'm going to give you the reference. It starts with 3,000 years. Sorry, my bad memory. Oh, 3,000 years of algorithmic rituals. Yes. It starts from the emergence of algorithm from the rituals, such as this one. This was a ritual in which they reconstituted this figure of a god from a series of bricks. So this very simple operation of reconstitution of construction implied the development and transmission of instructions. First of all, orally. And this kind of oral transmission of instructions that are practical instructions, not really drawings or blueprints, because the drawings came later. Initially, it was like this oral tradition that took hold. And there's a lot of this in self-construction communities, also in the Muslim huts in Cameroon, you can find that, and in other sorts of communities. So these instructions were actually construction algorithms. So instruction to build something without having blueprints. So the idea of machine, it's not necessarily related to physical machines. It becomes more and more abstracted and related to algorithms and the conceptions of rules. So leaping forward to John Fraser and the book An Evolutionary Architecture. So Gordon Paskin, in the preface, in the foreword for the book, says a very important thing. It says that the role of the architect is not so much to design a building or a city as to catalyze them, to act that they may evolve, which means, in other terms, something that also Cass Oster is phrased in kind of similar words. Instead of designing the object, you design the systems that makes the object. And if you evolve forward, you kind of start designing not just the system, but you design the rule with which the system works. And then you start abstracting more and more and having a different perspective on design. So instead of taking care of every single piece or aspect, you design a system that is capable of expressing certain qualities. So these are examples from John Fraser himself. This is a system that he started thinking about and designing in 1968. It's called the REP-tile, the repetitive tile system. And it's based on just two kind of pieces. But as you can see, it's a constructive system made to build structures. But the interesting thing about this system is that it allows an incredible amount of articulation. So there's not just the repetition of an object that makes the result looking like a tiled, let's say, a square tiled pattern that is very regular and very boring, but there is something else in the organization of the entire thing. So there's one aspect that regards the objects, the parts that constitute the system. But then when these parts get together, according to how they are organized together, they give birth to different conditions, to a heterogeneous set of conditions that exceeds the properties and the qualities of the parts alone. So a system in general is always comprised of two things, the parts and the relation between the parts. So there's one part of the complexity of the system that is related to the parts, how many they are, how complex is their design, how complex is their geometry. And the other part, and the other side of the thing is the complexity of a system can be due to the complexity of its relations, which means how the parts relate together, and this leads to what kind of organization can be expressed by a system. So in this case, the complexity of the system is a lot due to the possibility of organization that are enabled by the geometry of the parts. This is a very important aspect for our workshop, because we're going to work with these things in mind. So you will be designing some parts, some very elementary parts, and trying to look into the complexity by means of the rules and the organization. Because then you'll see what this means on a larger perspective. So going on with our quick history, the idea of building a machine and automating tasks was persistent in history. And at some point, with the birth also of other philosophies of space, or like the period of the geographers or the situationists, Johan Friedman thought of the flat writer, which was an algorithm meant to design apartments. So it was a tool to design a whole made out of parts, but it was a tool that was designed also with a participatory intent, which means it was meant to be released to the people so that the people could design their own apartment. And a similar intent was being developed at MIT in those years under Nicolas Negroponte. There was the architectural machine group that came up with a few interesting things. One was exactly dedicated to Johan Friedman and its flat writer, which is what you see on the left. It was part of a paper called Architecture by Yourself, where they built a program with an interface that was designing houses layouts, starting from a functional diagram, what you would call a sort of a force-based diagrams that you can see on top. You see that some sort of spatial bubbles that are pressing against each other, fighting for prevalence in a 2D environment. So you have a sort of topological diagram of how the functions or how the functional units were connected together, who should be connected with whom. And then according to their importance, they kind of assumed a layout in space, and then a layout of the walls was generated later. And this could be, again, in the mind of Negroponte, could be driven by the user. On the right, another kind of machine called Urban 5. It was under the same spirit, but applied to the urban level. The topological aspect, which means how things are connected and what is their continuity, it's another aspect that was investigated and applied by Johan Friedman for the design of this lycée, le Lycée David d'Angers, which is a lyceum for a school for the city. In this slide, you can see how all the concepts that Johan Friedman was developing for the flat writer, he was trying also to apply them to the design of a public building, a school. So there are models, there are repetition, but there is also an attention for the aspect of how these spaces are connected, what kind of structure do you get out of it. So these are technically what you might call graph. And they are let's say they put in an explicit way, in a readable way, what is the internal connection structure of a system. So you can think of this in terms of circulation spaces. So if you want to go from one place to another, according to, if you think that any room can be translated in abstraction into a point in this graph, all the connections give you the only way you can go through to go from one point to the next. So according to the shape of the graph and how a graph is connected, you have several possibilities, and certain nodes might be more or less important according to how much they are needed to go from one place to another inside this graph. So the topological aspect, actually, when you explicit it and you put it in a graphical form, can become a very important aspect to consider for how, let's say, things flow inside a system. In this case, inside an architectural system. And you can think this flow in terms of general information. And this information might not be just in coded form, like expressed in numbers. But you can think of any sort of things you can quantify as information. So even the flow of people, even your circulation, the heat circulation, the HVAC system, anything that needs to travel through there. You have an expense of energy if you want to go from one place to the next, and then you can quantify and make sense of how a certain diagram might be more or less convenient, or where the distribution of resources is going inside the structure. So you can consider different topological structure and consider how the computation of data in this more articulated structure is taking place. Later on, let's jump a few decades. This is one of the experiments that I think are mostly forgotten when it comes to the history of computation and architecture. There was this experiment in induction design, it's still ongoing, by Makoto Sei Watanabe. So in the 90s, it started to think about what's called induction cities. And it was literally saying in one of his books that the architect should at least tie one of his hands behind his back, meaning that when you design an algorithm, you should resist the temptation of just manually altering the results, and just work in the process that if there's something that you want to tweak in the result, you have to tweak the algorithm, not just manually shape whatever you like, because then you have to let the logic of a machine play out. And then you can evaluate it, of course, but if you want to look for alternatives, your place of action as a designer is in designing the algorithm, not just acting exposed on the piece itself. And so he had several urban machines, so to speak. One was called the Sun God City, because the development of neighborhoods was related to how much solar reach they had. So there was an algorithm that was growing cities to maintain an equal access to sunlight. Or another one which was called Wind God City, which was actually a simulation to try to build or design neighborhoods with equal access to natural ventilation, and so on and so forth. Coming to the present days, there are several people now that are researching in this in the same let's say in the same fashion, which means looking at sort of a mereological approach to this. Mereology is the study of the relations between the parts themselves and the parts to a whole. So it's a focus on not designing a whole from the get-go, but designing the parts, designing their relations, and see how these things play out, and how can you generate new conditions on the whole, or emerging condition on the whole, by designing and designing the parts and the relation they can have to each other. So this is an example from the large city architecture, which is a study by Daniel Kohler on an urban scale. Or on an architectural and constructive scale, there are very well-known experiments by the Bartlett Design Computation Lab, led by Girotzen, Molly Claypool, Manuel Jimenez Garcia, a lot of people that are working in this direction. And they are explicitly going into the scale of the constructive part. So we will look at kind of a different scale, because my interest right now is a little bit shifted in focus, not on a constructive level, but on a spatial level. So what we are dealing with are assemblages. And I want to take a few minutes to define assemblages. Of course, the definition opens up a philosophical Pandora's box, full of a lot of things, but I'm trying just to briefly make this introduction to put you into the mindset. But of course, for whoever would like to get in deeper into this concept, I'm preparing also a reading list that you can get after the workshop, because I will fill it up and complete it as we go, so that at the end of the workshop you will have more time to read and go through it. Or maybe you already know the concept because it has been for quite a while in the philosophical landscape of architectural development in the contemporary agenda. So assemblages is a concept that comes from Gilles Deleuze, and it was developed by Manuel de Landa later. So let's think about it in terms of these three paradigms. So you have the two paradigms at the extremes, so consider them the extremes of a spectrum. So on one side, you have juxtapositions in which the parts are completely dominant, which means each part is an independent object. The relations are irrelevant in meaning that even if you put the parts together, they keep their own identity in a strong way, which means you can still pick them out and separate them. So that would be the classical order, in which the capital, the column is always a column. You can put it wherever you want, it will always stay a column, and you can identify it very precisely. Their identity is immutable because they are already specialized in their function. They are, so to speak, finalized. On the other side of the spectrum, that's the organicist metaphor, where parts become completely irrelevant. What is relevant is the whole. The parts fuse into the whole and completely lose their identity. They are meaningless compared to the whole. So they are, let's say they melt literally in the case of the Physarum polycephalum, which is the picture that you see there with the slime mold organism. It's made of billions and billions of individual organisms, or individual, let's say, cells, but they constitute a single organism. So in the middle, we have assemblages, in which parts have their own identity, but when they are put together with other parts, they can shift and mutate this identity and become something different or something more. This is because objects have this internal and relational characteristics. So they have what the Landa calls properties and capacities. So a property would be something that it's of the object itself. The capacity is something that is expressed just when it comes into relation with other objects. So the Landa always likes to do the example of the knife. Speaking of a knife, a property would be the sharpness or bluntness of the blade. This is something that you can measure as the angle of the blade compared to the middle axis. So if the angle is very narrow, the knife is sharp. If the angle is wider, the knife becomes blunt. So that's a property. So it's of the object. It doesn't matter where you put the knife, it will still have the sharpness as a property. And then there are capacities, which is the capacity of a knife to cut or do not cut something, which depends on the capacity of another object to be cut from that knife or not to be cut. So the knife, according to how the knife is made, it can be able to cut paper or to cut steel or to cut rubber. And this depends on the capacity of paper, steel, rubber to be cut in reverse by the knife. So long story short, the thing is, while properties are limited, capacities are open-ended because there is no way to predict how many possible relation an object can have with every other possible objects. So this opens up the possibility for emergence and an open-ended horizon, because it doesn't matter when you have a part on its own. It's when you start to putting it into relation with others that these capacities start to play out, and the possibilities of this part to become something more inside a wider organization, they start to become possible. They materialize somewhere. So the idea is to look for something that is defined as a heterogeneous space. And this is why the parts that you will be designing would not be at the scale of constructive part, but at the scale of architectural space, like something able to contain people or to be traversed by people. So it's not a concept of difference that we are looking for, that it's produced by form. We are not looking for difference that is there because you take parts that are all different from each other. Then you will make just an unrelated collection of things. And they will be not just difference, but diversity. Not something that is just produced in an overall void by just putting things in a sort of unrelated positions and hoping they play out. In our case, we're going to work with a concept of space that will permit discontinuity and differentiation of both qualities and organization with a condition that will emerge from how you're going to write the rules of how parts are coming together. I'm going to give you some examples right away so that you are not like left in a bubble or left in a void with this very theoretical slide. For the time being, just take note of this. It will become clearer with the examples themselves. So the core idea, we're narrowing down to the very core idea, which is the diagram that was put on the workshop Instagram somehow, is that we are going to treat our parts as our, let's say, discrete parts or discrete components as spatial computing units, which is units that are able to compute space for flow of information, and they will form a complex nonlinear network. So the analogy of the transistors might be a little too literal as a form of interpretation, but it doesn't have to be, I mean, that literal. It's just a diagram that helps make sense of this way of proceeding for the moment. Because if you think about it, now we are used to thinking about computation in a very abstract term, but if you go to the very nuts and bolts of it, it's still what you see in this diagram. There are still physical transistors that let electricity through or not, according to their internal physical structure. If you can call them that without doing any disservice to the term, the internal architecture. It's not a sense that they're called computer architecture. There are actually topics about CPU architecture. It's not a chance that it's called architecture, because in the end, it has to do with spatial distribution of things. And the way that transistors are connected together, I mean, in this case, you can see this as a very close analogous to the Yonah Friedman's topological diagrams, because they make sense of how the nodes are connected together. If you want to get from one node to another, you have constraints and possibilities. And these elementary pieces, they are processing the flows to open or close gates for the electricity to flow to the next transistors. And even the most complex computer program, it's still made of these elementary pieces of computation. It's just that when you write a program, you build more and more complex organization of these elementary code blocks. And then you build more complex code blocks that repeat themselves, and you proceed by clustering and organizing things. And what you get in the end, it's a highly complex architectural organization of things that allow you to compute very complex things. So the idea that we are trying to explore is how can we think of an architecture that applies the same principle, which means considering the architecture that you are producing through the assemblage of parts as a computing object in itself, and consider how the structure, the topological structure of that object, according to the design of the parts, according to the organization of the parts, performs or is able to perform in terms of computing these flows. Primarily flow of people. We're gonna just look at one very simple aspect, which is circulation through some things that we do with the design and with the code. But it's going to be interesting to see how, when you build something and you expand the topological structure that you're building through the code, the computational capacity of the object that you're building can be at least observed. And we'll find ways of observing and also performing operation that you can perform just because you have that object specialized, and you can use it to compute things. I will be more clear both in the examples and as we go through with the workshop. It's getting, we're 15 minutes to 10, so I'm going to accelerate a little bit. So the idea is, like I said, conceive discrete components as spatial computing units for a flow of information in a complex nonlinear network. What we will produce will be exactly nonlinear networks in the end. So what's the difference between, let's say, a unit or a component part? We're going to deal with components or parts and not units. What's the difference? Take the Habitat 67 by Moshe Safdie, for instance. This is an example of the use of a unit. So it's, let's say, you can say it's a prototypical example, historical example of a form of assemblage. And what is interesting, it's actually the intricate structure of a space that you can see through the section. But you can see that it's a combination of the same kind of units, which was also thought for accelerating and speeding construction. Interesting to do that, he had to be highly redundant on structure, so every single piece was a load-carrying member as well. So there was a lot of redundancy in that. But the thing is, it's still based on a functionalized, finalized unit that combines with the other. So it doesn't matter how many you put together, how many you put them in relations, there will be still, let's say, enclosed capsules, functionally speaking, that do not give rise to a different condition of space. It's the same condition of space repeated over and over. What you can have as an emergent condition is what's left outside. So it's the public space, is the space that's not inside the housing unit. So the difference between component part and unit is that the unit is functionally predefined, functionalized, and also contained. What we are working with, component parts, are going to be unspecified. So you will work with very generic spatial parts, not assigning them a particular function, that are capable to acquire further properties in an assemblage. What you see on the right is, let's say, a shape grammar for some parts that are part of Froebel toys, something that Frank Lloyd Wright used to play with also. But you can, the important thing is that the same parts are permutated over and over, and according to their location in a new kind of assemblage, they acquire potentially different meaning, and they give rise to potentially different conditions. Just for the fact that they are, first of all, unspecified, and second, they are open to form larger condition and not contained. I don't remember why, yeah, okay. We're going to rely on something that is a process of distributed decision and rely as the least possible on randomness. which is an important distinction and difference. And also important is to understand what is the difference between linearity, complicatedness, and complexity. So in terms of, let's say, topological qualities, what makes the difference is the figure on the right. The figure on the left and the figure on the middle, topologically speaking, are exactly the same things. It's a linear connection. It doesn't matter how convoluted it becomes, but it's still a linear connection, because if you think about the 2 pointers A and B, all you can do is go from A to B or B to A. This is like the linear paradigm, which is predictability. I am in A, the only predictable thing I can do is go to B. I am in B, the only predictable things I can do is go to A. If you put a lot of this in a chain, it doesn't matter how long the chain is, the whole process is still predictable. And then you can calculate, if you go from A to Z with a chain of this simple connection, by having one connection for each, the whole process becomes still, it doesn't matter what shape it takes, it's still linearly predictable. What changes is the figure on the right, because you have something different, which is a bifurcation. The bifurcation means that at some point you have to make a choice. You have to make a decision. Think about the three extremes of ABC. It doesn't matter from which extreme you start. At some point you get to the bifurcation and you have to choose whether to go left or right, or front or back. I mean, it's a matter of orientation, but let's say left or right for simplicity. So think about distributing these things in a network, like thousands of these things, or millions of these things, like in a brain. And think about that the cells in the brain do not just have bifurcation, but they have multiple ramifications. So the decision becomes even more complex, right? To predict the behavior of the system, even if the decision is deterministic in its granular appearance. I mean, in this case, the decision, once you have a criteria for the decision, there is no uncertainty. If I put a criteria, then I think I know that the criteria is met, I go one side, the criteria is not met, I go the other side. You can distribute this in a network and still have a system that is very hard to predict, because the possible combinations, to predict a system like that, you have to put on a table all the possible combination that a signal can do inside the network. And this can grow very, very quickly out of hand. Thinking about the example, Claude Shannon makes the example of the game of chess. So yeah, you can build a computer with all the possible moves in a game of chess, but the entire matter of the universe would not suffice to build that computer. That complex this is how things can become complex. So if you search for a Shannon number, I think you will find this example of the game of chess. But you can, let's say, instead of going to the predictive stance, going to a simulation, which is build a system that has that complexity and see how the system plays out. So our logic would be to design parts, design connections, and then write the rules that allow one part to be connected to one part of how the connection go together, right? Not exactly in this way. This is a very simplified diagram still by large city architecture. We're going to deal with something like this. I will come back to this slide later on when we reach the point in which we have to write the rules. I will explain in detail what everything is, but for this initial introduction, this initial inception, think about that we're going to have components that will be our geometry. Then you have these connections that you will design, and then you will design a rule or a syntax to bring one connection for how the connection are going one to each other or together. So there are several examples. This is from Roblox, if I'm not wrong, from the Bartlett. The part design is very simple, and you have like two kind of possible connections. The one in light blue, the one in pink. So the different types can only go with the same type. So light blue can only go with other light blue, and pink can only go with other pink. And then you have possible combinations on the right. And some examples of how, by following different rules, you get to different expressions of the system. Or introducing progressively different rules, you get progressively, let's say, a more articulated expression of the system. The interesting thing is that this kind of object that you're seeing, it's all constituted of the same part, just repeated over and over. But by changing the organization, the overall complexity of the system and the recognizability of the complexity, which is another important aspect, gives you a different expression. So that's another example from the large city architecture, in which they are experimenting, in this case, with semi-functionalized parts, let's say, because there are parts that are recognizable as connectors, parts that are recognizable as containers. But then according to how they are put together, they can form more or less dense connection, they can form courtyards, they can form other emerging conditions. Still, when put into a larger system, they can express some meta conditions on a larger scale. So it's not just the part and the whole, you see the emergence of an intermediate order. So you can see the emergence in this case of walls, but the system doesn't have any element defined as wall. It's just because of how the parts are put together. So this was one of the examples of some of my students, and it was interesting. It was like, this was just an intermediate review, but just because of the parts that are on the top right, you have a sort of a catalog of possible architectural and spatial conditions that was incredibly extensive and incredibly well differentiated. Other examples from students of mine. This is a more complete example because that was on a finalized project. So this was one of the parts this was the part they chosen to work with. As you can see, it's really, really simple. It's really elementary. And then they wrote all possible combination and orientation. The interesting thing is that this part can be oriented in all directions of space by 90 degrees rotation, but it's not just a pavement or a wall. It will become a pavement or a wall or a ceiling according to its orientation. And then they started to write the system connectors and experimenting with all the possible combination, also disregarding something that they didn't like or they couldn't play out well, and also designing how the system grows in complexity by adding more and more rules to it. And then starting to look at what kind of spatial conditions the system was making, just by the effect of the simple part, and starting to make a distinction that is already ingrained into the design of the part between several subparts. So the part is comprised of some subparts, and then you can distinguish how they have been distributed into the system, and according to that, take some actions. Or actually design into the part some potential additional element, like these ones that you see in yellow and red. And then according to the assemblage, decide where these additional subsystems come up or not. So these subsystems in yellow and red are, let's say, optional subsystems that are still part of the design of the component. And then according to the general assemblage, you can decide according to the condition that one part has ended up with to put some of these extra objects or not. Let's say I'm going to put this only if the part has landed vertical, or only if the part has landed horizontal, or only if the part is close to a frontier, or only if it's connected with certain parts. So it's not just something that is still at the part level. It's a property or a capacity of the part that comes up in the conditions in which you have in the whole. So these are some of the final results of this project. These were like two instances of the same thing designed with the same system. The idea was to design these two cable car terminals exactly with the same system. That was another project exactly on the same topic, but initially they did a larger exploration. Again, this is made out of a system of parts that grow from a very elementary one. These are like really two planes perpendicular to each other, and then the other parts are just growing a little bit from that. They decided to use this 5 type of parts and subparts to design the system. So you can see by the scale of the person on the bottom left, which is more or less the size and scale of spaces, but it's still unspecified spaces. All of these are unspecified spaces. And then you can perform a sort of analysis, like looking at how much walkable surface or continuous surface you have created at each level. And then you can, by effect of this analysis, perform other forms of analysis, or, for instance, analyzing circulation and decide where you want to add connectors from one level to the other. And then, according to the possibility of the part to host this kind of connectors, you can decide where to add them and where selectively add them to the system. So studying circulation, study where to include the elevator shafts that the system allowed, not just the drilling hole through, but understanding how the system could also move around this elevator shaft that you can place in advance. So this was kind of some of the images of the final result of the object. These are other experiments that the students at IAC in Barcelona have done under the guidance of Andrea Graziano and myself. Still the same kind of logic, so exploring the assemblage of parts, and then in this case looking at what would be some of the possibility of a shortest path going from bottom to top in this complex situation. So what would be the shortest path, and what part will it traverse to get there? So you can scan the system, analyze it, see how it grows in terms of your rules, and then performs also some analysis. These are other analyses from large city architecture, or in this case, this from the RC4 at Bartlett. You can, once you have done the assemblage, you can look for the spots where to place, for instance, additional walls for stability or for any other criteria. In other cases that they are also, in one of the latest projects that Giretsen has done, there are also moving parts, like rotating walls that can close or open spaces. These are other forms of analysis that you can perform. It's just to show that the final object is not the end goal, but it's actually a middle step in the process of then post-analysis and other forms of action that you can use computing through the object itself. This is another example of, let's say, a simple part that for its own properties, it's also analyzed in its connective properties. And then you extract this network of topological connections, starting from the design of a very, very, very simple parts, but then the connections and the possibilities of the parts allow you to do this, or to build this more complex object. More circulation analysis. I think I'm out of time. So yeah, more or less. We were done. I'm just gonna scroll through to see if there were some more interesting things. Well, no, we can talk about this a little later or even tomorrow. So for the for the moment, I'm gonna let you free if you want to follow some of the lectures of Digital Futures that are happening now from 10 to 12. And I'll see you again at 12. That's okay?
Yeah, all good.
So yeah, so if you want, you also can have time to note down some questions that you might have. And we're gonna do, let's say, question and answer and finalizing the setup at 12, right? One last thing, I'm gonna send you an email with the material to download. It's really like 4 megabytes or something. So, but just while you're following lectures or doing whatever you prefer, you can download the material. So we are ready for the next step. Okay?
Cool, thanks.
Thank you.
Thank you very much. And I'll see you again at 12, right?
Yes.
Okay.
Yeah.
Yes.
Bye.
Okay. Let me see. How can I stop this? Right.